Hi everyone, welcome to the Arithmetic Zone. This is part 3 in our series on the unit circle. So if you haven't watched part 2, I strongly recommend you do so, since in that video we went through the process of constructing the circle that you see on your screen right now. So in this video, part 3, we're going to be going over some basic trigonometry and see how it relates to the unit circle. So I have this example here to supplement what we're going to be reviewing, and I apologize for the printing error, but consider the isosceles right triangle, whose side lengths are equal to 1, the square root of 2 over 2, and the square root of 2 over 2, respectively. Find the exact value of the following trigonometric expressions. And we see cosine of 45 degrees and sine of 45 degrees. Now, we're going to have to go back to some of our geometry level trigonometry. And you may remember this acronym from geometry. It's called SOHCAHTOA. I'm writing it in a bit of a weird way, but it's just to emphasize the different aspects of SOHCAHTOA. So let's look at this. So the S stands for sine, and it's going to be sine of some angle theta. The O stands for opposite. I'm just going to write op over hypotenuse. Now, cosine, that's what the CAH starts off with. Cosine of theta is equal to adjacent over hypotenuse. And finally, the TOA part, this stands for tangent of theta is equal to opposite over adjacent. And it's important to note that SOHCAHTOA only applies to right triangles. If you don't have a right triangle, then the relationships established by SOHCAHTOA are not applicable. So now we can go along with answering the question. So we see cosine of 45 degrees. This is basically our cosine of theta, theta being 45 degrees, is equal to adjacent over hypotenuse. So let's identify our 45 degrees. Now there are two 45 degrees. It's going to work the same no matter which one you choose. So I'm going to have our focus be this guy right here. So adjacent just means what is the side length adjacent to this angle? What is the side length right next to the angle, if you will? So that is the square root of 2 over 2 right here. So this is equal to the square root of 2 over 2. And this is all over our hypotenuse, which is 1. So the square root of 2 over 2 over 1, and that's simply just the square root of 2 over 2. Now sine of 45 degrees. We're going to use the SO part of SOHCAHTOA. So sine theta, where theta is 45 degrees, is equal to opposite over hypotenuse. So this is really equal to, let's focus on our 45 degrees. Opposite of 45 degrees is square root of 2 over 2 again. Square root of 2 over 2. This is all over the hypotenuse, which is still 1. That never changes. This is also equal to the square root of 2 over 2. Now let's get another example. So we're going to consider the scalene right triangle whose hypotenuse is equal to 1 and whose side lengths are 1/2 and 3 and the square root of 3 over 2 respectively. So let's label that. This down here is 1/2 and this is the square root of 3 over 2. And I don't know, you may have caught on to this, but this example that we just did and the example that we're working right now are the special right triangles that we worked with in the past two videos. So we're going to find the exact value of the following trigonometric expressions. And now there are four, sorry. So I'm going to write out our SOHCAHTOA here. TOA. And I'm going to go a little faster this time. So we're focusing on the 30. Whoops. We're focusing on the 30. We're doing cosine of 30 first. So adjacent, that's the square root of 3 over 2, over hypotenuse, which is 1. So this is square root of 3 over 2. Sine of 30. Opposite of 30 degrees is 1/2. So 1/2 over 1 for our hypotenuse, and that is 1/2. Now let's move on to our 60-degree angle. I'm going to circle this, cosine of 60. We're going to look at the side length adjacent to it, which is 1/2, over our hypotenuse, which is 1. So this is going to be 1/2. And with sine of 60, we're going to look at the angle, or the side length opposite of the angle, which is the square root of 3 over 2. over 1 for our hypotenuse. This is the square root of 3 over 2. Now, just an interesting thing to note is that cosine of 30 has the same value of sine of 60. And cosine of 60 has the same value of sine of 60. So it's just an interesting thing to note. We'll look at why this is the case a little later. So you might be wondering, why did we do this? Why did we go over this trig? And this kind of segues into our formal definition of sine and cosine. The so and the ka part of SOHCAHTOA. So I'm going to read out this definition, and then we're going to see what it looks like on the unit circle. So it reads, on the unit circle, if a line segment is drawn that begins at the origin and touches the circle, the x-coordinate is equal to cosine theta, and the y-coordinate is equal to sine theta, where theta is the angle the line makes with the x-axis. So that's a pretty loaded definition. So I want to focus on a couple aspects of this definition. So on the unit circle, a line segment is drawn that begins at the origin and touches the circle. So I have a copy of the unit circle right here. It's a circle that we have already drawn in the past. So I won't go through the process of I won't explain everything, but we're just going to have this line that starts at the origin and touches the circle. That's what that blue line is. And I'm just gonna go quickly to the end here, where theta is the angle the line makes with the x-axis. So now let's label that here. This is the x-axis, this blue mark. And this is going to be our theta, which is going to be 30 degrees. That's what this is. So once we have that, we can see that the x-coordinate is equal to cosine of theta, and the y-coordinate is equal to sine of theta. So if we go back to our example here, we can say that sine of 30 is equal to our y-coordinate, and that's going to be 1/2. And cosine of 30 degrees is equal to our x-coordinate, which is the square root of 3 over 2. This is one of the fundamental properties of sine and cosine, and it is super important when we go into trig, because this is how you solve certain trig functions like sine of 60, let's say, without a calculator, 60 degrees. Because if just knowing the unit circle, sine of 60, oh, let's look at the y-coordinate of the coordinate associated with 60, square root of 3 over 2. So I have here labeled the equation of a circle. It's x squared plus y squared is equal to 1. That is a general equation of a circle, and more importantly, the equation of the unit circle. So if we know that cosine of x, cosine theta corresponds to x, and sine theta corresponds to y, we can actually sub in cosine and sine in for our x and y. So I can have cosine of x go in there, and sine of x go in here. And that's where this equation comes in. Cosine of x, oh, let me make that a bit bigger. That's where we get cosine of x plus sine squared of x, or cosine squared of x of theta plus sine squared theta is equal to 1. This is what's known as a trig identity. This is one of the most basic trig identities that we can derive from the unit circle. And there are entire math classes dedicated to trig identities. So knowing this sets the foundation for some really higher level math. So I'm not going to go over all of the coordinates. We're really only going to focus on quadrant 1. So here we have our angle in degrees, angle in radians, sine and cosine. And this is all of the y coordinates and all of the x coordinates. I wrote it a bit backwards, so I do apologize for that, but that's our x and y. So all of these angles have a coordinate point that corresponds to it. And from those coordinate points, we get sine of the, we get sine of the angle and cosine of the angle. So now let's look at tangent on the unit circle. So we need to remember that tangent of theta is equal to sine theta over cosine theta. So if we know the value of sine theta and cosine theta, it's pretty simple to get tangent theta. And we just discussed that sine corresponds with the y coordinate point, and cosine corresponds with the x coordinate point of some given angle. So using that, we can also derive the tangent of any angle on the unit circle. So let's go over an example. We'll start off with tangent of 0. I'm going to try and make that align better with the x-axis. Yeah, that's good. So let's look at tangent of 0. I don't have to specify degrees or radians because no matter what, it's still 0. So we're going to have sine of 0 over cosine of 0. So I want to focus on these coordinate points, our x and our y. Our y is 0 and our x is 1. 0 over 1 is 0. That means tangent of 0 is 1. We can also look at tangent of 30 degrees. I'm going to specify the degrees because that's important. This is going to be equal to sine of 30 degrees over cosine of 30 degrees. So now we're going to look at these set of coordinate points, this being our x and this being our y. So we're going to have the y on top with the sine. So it's going to be 1/2 over the square root of 3 over 2. Now we're going to simplify this a little bit. So we're going to do 1/2 times 2 over the square root of 3. This is the technique called keep, change, flip. This is how you divide two fractions by each other. You could also multiply by the reciprocal. That's basically what I'm doing, but I like to abide by the acronym keep, change, flips because it just helps me visualize it better. So these twos cancel out, and we're left with 1 over the square root of 3. And if you remember from our previous videos, we don't like to have this rational or radical in the denominator. So we're going to take 1 over the square root of 3. And we're just going to multiply it by root 3 over root 3. These two cancel out, or whoa, that's not true. We're going to have the square root of 3 over 3. That's what tangent of 30 is equal to. And of course, you can go all around the unit circle and derive all of the values of tangent, but we're just going to focus on quadrant 1 and for good reason. So now we can reveal our tangent of x graph. This is all of the values of sine, cosine, and tangent as it relates to quadrant 1 specifically of angles and degrees. Now, if we go over to quadrant 2, 3, and 4, the values of sine and cosine and tangent change a little bit because of the different properties of quadrant 1. If you remember in quadrant 1, everything was positive, so there's no problem there. But as we get into the negative world, we do have to account for changes in sine, cosine, and tangent. And that's what we're going to look at in our next video, and hopefully our last installment where we can graph sine of x, cosine of x, and tangent of x, the function equivalents of what we have here. So thank you so much for watching, and I hope to see you next time.